This is part 10 of a series of videos about multivariable calculus using the computer program called Mathematica. What you see here is actually what's called a Mathematica notebook in which I can do calculations with Mathematica. It's part 10 of a subseries on calculations with parametric curves. Parametric curves come from parametric equations, which are useful in modeling motion. In the last video we looked at a motion and tried to figure out the speed of the object as a function of time, and ultimately also the distance traveled by the object as a function of time. We're going to do the same thing here with a new kind of motion. This motion is going to be a motion that spirals in toward the origin. And we're going to try to figure out something kind of interesting about this spiral. We're going to try to figure out whether it's of finite length or not, corresponding to whether or not the distance traveled is finite or not. So here's our example. And if you look at the equations here, it's not so surprising that this is going to be a spiraling motion. You've got some exponential decays that are going to go towards 0 as t goes to infinity, and you have some trig functions, cosine and sine, that are going to oscillate as t increases. This is going to result in a spiraling motion toward the origin as t increases. We want to determine the speed of the object as a function of time. That's the first thing. Second thing, we want to find the distance traveled by the object as a function of time. The third thing is our interesting question. We want to answer the question, does the distance traveled have a limiting value as t increases to infinity, as t gets arbitrarily large? The answer will be yes or no. Finally, part D, we're going to make a graph that shows all this. The motion is going to be on the left, and the speed and distance traveled will be shown in a graph on the right. I've got the Mathematica code already in here that I need. If you want some information about how I constructed this, you should watch the preceding videos. We are again in video 10. So I want to enter these functions into Mathematica. Something new in this video is that I'm going to be entering an exponential function, the number e. There's actually 3 ways this can be done in Mathematica. I could type in f of t like this. I could use exp with a capital E and then square brackets negative t over 10 to represent e to the negative t over 10 power. That is one way to represent that, times the cosine of t. Notice, again, the capitalization is important and the square brackets are important for function arguments. Here I'm really thinking of e to the x as a function. Another way to do that that emphasizes that the negative t over 10 is in the exponent is to type it like this, capital E to the negative t over 10 power. Notice I'm using the up arrow, and I'm using a power that's inside parentheses. It's no longer a function argument. You think of this as being a power of this capital E, and capital E does represent the number e in Mathematica. A lowercase e doesn't work. Mathematica treats that as a variable, essentially. Yet one more way to do this is to either use this basic Math Assistant palette over here on the right, or use a trick to get this fancy looking e to come in here. And the trick is to hit escape, then 2 e's, and then do escape again, and it magically turns into a fancy looking e that represents the number e. I typically use a capital E, that's quicker, so that's what I'll do here. My second coordinate, g of t, is e to the negative t over 10 times sine t. And as you know, if you've been watching these videos, I like to put these things together in a list, and I plot that list as a point with parametric plot down here and list plot. Alright, so this stuff is going to be entered. I also want to enter the speed as a function of time. And as I've shown you recently, the last couple videos before this, you find that speed by taking the square root of the sum of the squares of the derivatives of these coordinate functions f of t and g of t. This is going to give you the speed. You should take the time to stop the video and use these functions and this formula to figure out how the speed does depend on time. It's going to be a kind of a complicated calculation. You're going to have to use the product rule and the chain rule. You're going to have to square out the derivatives of these things and add them together before taking the square root. It will be fairly complicated. You'll get some cancellation. You'll also have to use a trigonometric identity that you should know. It's one of the most famous ones. What should you get? Does Mathematica simplify this? Actually, Mathematica doesn't simplify it right away. It writes it like that if I just type speed of t. But if I embed this in the command simplify, then it does simplify it down to this, though that's probably not how you're going to write it if you actually do the calculation yourself. You are probably going to write it more like this. first of all, as a fraction, the square root of 101 over 10. And secondly, a more traditional way to write the square root of e to the negative t over 5 would be to write it as e to the negative t over 10, because when you take the square root, that's like raising it to the 1/2 power, and you'd multiply the 1/2 times negative t over 5 to get negative t over 10. So I'm not quite sure why Mathematica did that, maybe because of the square root here, but this would be the more common way to write this. And I'll go ahead and enter it this way as is. What about the distance traveled? From the last video, you should recall that the distance traveled as a function of time is found by integrating the speed, take an equal sign there. We're starting our motion at time 0, so the lower limit of integration is going to be a 0. We're letting time go by, t seconds of time go by from 0 to t. The upper limit of integration has got to be t if I want to write this as a function of t. And you integrate the speed. Now some people are sloppy here and go ahead and put a t in the argument for this function here. I like to emphasize that the true variable for dist of t is in this upper limit of integration, so I use a different variable here. I use the Greek version of t, which is tau. Notice I can make that by doing escape, t escape. It makes it tau. In this case, it's not too hard of an integral to do by hand. We essentially, again, are just integrating this function, so we can do that pretty quickly by hand here. Square root of 101 over 10, that will come out in front of the integral. Integrate from 0 to t. And again, I can write this, I can do it the fancy way with escape, 2e's escape, negative t over 10. You can, and I'll use a tau instead of a t. And then, if you think about that, when you do that integral, you could use a substitution, u equals negative tau over 10, or tau over 10 for that matter, and get negative square root of 101 e to the negative tau over 10, and you've got to evaluate that. Tau goes from 0 to t, and if you do that, you should get, let's see, square root of 101 times 1 minus, in parentheses, e to the negative t over 10. When you simplify that, we can check this with Mathematica. We can define dist of t via an integral like this. And then we can enter it and see what Mathematica spits back as the formula for dist of t. And it does give us the exact same answer there. I'm actually going to copy and paste this and redefine dist of t by this simplified formula instead of the integral formula, because if I use the integral formula when I want to go ahead and plot it, it might slow Mathematica down a bit because it'll be doing a lot of integrations. So if I just go ahead and type in the formula like this, it's now entered. What have we done so far then? We've figured out the speed as a function of time. Its units would be meters per second. We figured out the distance traveled as a function of time. This thing, its units would be meters. The last two things to do are to figure out the whether the distance traveled has a limiting value as t goes to infinity or not. And we also want to make our graphs. Let's actually look at the graph first and see if we can guess the answer about the limiting value based on the graph. So here's the situation. We've got the motion of the object spiraling around toward the origin on the left. It spirals forever and ever as t goes to infinity. And on the right, we've got the distance traveled in blue and the speed in red. You do see the speed decaying towards 0. The object is slowing down as it moves toward the origin. The distance traveled is increasing, however. Does it have a horizontal asymptote is the key question here. Maybe if we go out further, we can see more clearly whether it does or not. I'll go out to 60 pi instead of 6 pi. Let's see, okay, that motion's having more difficulty with it. It looks like it probably does have a horizontal asymptote at t equals 10 perhaps. Can we tell that from the formula? Yes, you should be able to. The answer to part C is yes. Yes, there is a limiting value to dist of t. In fact, you can say by looking at this that since e to the negative t over 10 goes to 0 as t goes to infinity, dist of t goes to square root of 101 as t goes to infinity, a little bit bigger than 10. Alright? So even though the spiral goes around the origin infinitely many times as t grows without bound, the distance traveled approaches square root of 101, just a little bit bigger than 10. It never gets past that, and it does approach that number in the limit. Alright, kind of interesting. Infinite number of spirals, but a finite length. Here's your exercise. Your exercise is basically the exact same example, but a bit more general. I've got a couple of letters in here, A and B, that represent constants. You want to assume they are positive constants. And you want to do the exact same thing as in the previous exercise, in the previous example, treating A and B as positive constants. So here's my solution. Zoom in a bit here. For the speed function, I did things by hand, so to speak. It should simplify to this expression. That'll be the speed as a function of time. The distance traveled should simplify to this expression, or if you prefer, you can also write it as this expression. And as long as A and B are positive, as long as A is positive, so that e to the negative at goes to 0 as t goes to infinity, there is a limiting distance. It does depend on A and B. This quantity right here, that is the limiting distance. And we can actually get this in Mathematica in an even more interesting way than I've shown you. You can treat A and B as animation parameters as well. So not only do we see a motion, where I'm using a capital B here to be time representing this motion, but I also can change the values of A and B and change the nature of the motion and how fast the spiraling is occurring and how fast the decay towards 0 is happening. And you can see the changes to the graphs of the distance traveled over here on the right. Okay, so that's kind of an interesting way to do it. Here again was the example if you want to look at it again.